Hello, everyone. Welcome to the last talk, not necessarily the last word of the conference. First of all, I would like to thank the organizer, specifically Shadab, for the invitation and giving me this opportunity to speak here. So most of the work that I'm going to present here were led by students from IIT Indore, and those names in blue represent essentially either former or present master's or PhD students. So before I start talking about Cosmic Dawn, there is a bit of advertisement. So I am from this part of India. Those who do not know Indore, it is probably the cleanest city, supposedly, consecutively for this will be the 7th year, I guess. It's 1,100 kilometers away from Bangalore. And we have a rather new IIT, some of these nice buildings that you can see there. But our most prized possession on campus is this 4-element interferometer, radio interferometer, essentially, which is operating at 1.4 gigahertz. It is mostly used for training the masters as well as the PhD students. So our department is also unique and first of its kind in the IIT system. We already have an established PhD program and 3 master's program running for some time. And we will be starting a new BTech program in space science and engineering starting from this July. So let's get into the business of Cosmic Dawn. And as all of the previous speakers have already explained why it's important and why we should essentially try everything to observe this particular elusive era, I will be talking about mostly the boring part, which Hamza said that is very difficult to observe. And so far it has been extremely difficult. So in this 21 centimeter signal that we are expecting from Cosmic Dawn and epoch of reionization, the radio interferometers, not necessarily the one I showed you, but ones like HIRAX or the ones that operate at even lower frequency would be targeting the fluctuations in the signal, fluctuations in space as well as in time. Here, the time converts into the observing frequency. So the 21 centimeter signal will get redshifted and will go to higher and higher wavelength. So if you look at the fluctuation, the brightness temperature fluctuation, there are terms from cosmology and there are terms that are due to astrophysics. And I'll be focusing mostly on the astrophysics term. And this astrophysics terms, one is due to the ionization of the intergalactic medium, and the other one comes due to various kinds of physical processes that go on in the IGM. I guess I'm loud enough so that I can be heard at the back. So during the Cosmic Dawn, these other processes are more important. So these other processes are Lyman alpha coupling and X-ray heating. They essentially change the relative population density in these two hyperfine states and gives rise to a signal in emission or absorption, depending on which one is more than the other. So our hope is that this astrophysical processes that go on in the intergalactic medium essentially make the signal highly non-Gaussian. Why it is so? First of all, the sources that produce these X-ray, Lyman alpha, or UV photons, they are not necessarily randomly distributed. They are located at biased location at the halos. And then the radiation that they emit that interact with the intergalactic medium, and it changes the physical processes that go on with time, and a new generation of sources are born, so on and so forth. So the fluctuations are not necessarily random. They are also time evolving. So these two things make it highly non-Gaussian. Okay, so the first part of this talk is about understanding how these two Lyman alpha coupling and X-ray heating essentially dominate over each other at different cosmic time, and how do they impact the epoch of Cosmic Dawn 21 centimeter bispectrum. And this work was led by a former PhD student, Mohammad Kamran, who is a postdoc now at Uppsala. So I think you have already seen this slide, and what we are essentially measuring here are Fourier transform of your brightness temperature fluctuation, 3 such delta 21 at 3 K modes, which essentially make a closed triangle. That's what bispectrum is. And we are essentially estimating an ensemble average of that quantity. Why bispectrum? Apart from the fact that it is going to probe the non-Gaussianity in the signal, bispectrum has an added advantage. Depending on the nature of the fluctuation, the sign of the bispectrum may change. It may be positive or negative, whereas the power spectrum will always be positive. That's a definition, nothing else. So now, once you start constructing these triangles in Fourier's domain, you would like to know how many types of triangles you can form, right? So you go ahead and try to parameterize the shapes of these triangles. And this can be parameterized quite nicely using this formalism, where essentially this tip of this triangle, if it rotates, it kind of maps within this shaded region in the parameter space, which is defined by the ratio of these two arms, K1 and K2, and the cos of the angle between these two arms. So if you keep the tip of the triangle within this, which you will if you have the K1 as always the largest arm, and K2 is larger than K3, et cetera, et cetera. So then essentially all possible triangles that you can form can be mapped into this shaded region here. And in this shaded region, this point here is the equilateral triangle, and this point here essentially is a squeezed triangle. This is isosceles, this horizontal line are isosceles triangles. So we will be focusing on only the squeezed one. Why the squeezed one? We have shown in our previous works that the squeezed triangle has the maximum amplitude. And also for future SK-like observation, you have the highest detection probability for the bispectrum for these kind of triangles. The third point is that if you target squeezed triangles and with small K1 mode, K1 is the largest arm, the way you have restricted your parameter space. So then you will be looking at the correlation in the signal at very large and large length scales. So if we are interested in the signal fluctuations at large length scale and non-Gaussianity at those scales, we should be focusing on this type of triangles. So that's the motivation. And with that motivation, we went ahead and tried to set up the problem. And to set up the problem, we needed to simulate the signal because there is no signal so far. So there, Raghunath Ghada essentially came into picture, and he used his 1D radiative transfer simulation Grizzly to give us the 21 centimeter maps. We do include the impact of peculiar velocity, so redshift space distortion are taken into account. And we remove the average of brightness temperature from these signal cubes to mimic the typical observation that you would expect in a radio interferometric array, because you do not have the DC signal in the radio interferometric observations. So next, to set up the problem more clearly, what we did, we essentially thought about formulating 4 different models. First of them is this model A0, where we purposefully kept only Lyman alpha coupling. All the other physical processes are absent. In the second one, we have Lyman alpha coupling plus ionization. In the third one, we purposefully made Lyman alpha coupling saturated from the beginning. And then on top of that, we had X-ray heating as well as ionization. And in the third model, all 3 of these processes were included self-consistently. So in a single sentence, the first 3 ones are pretty simplistic. And the aim of building these models is to see their signature, the individual IgM processes signature on the 21 centimeter bispectrum. And then when we actually analyze the realistic scenario, we can identify what kind of signature we have seen already into this one. So there can be a one-to-one mapping, hopefully. That's the hope. And with that hope, we went ahead and started running our simulation and estimating the bispectrum. So in these maps, in the first row, the redshift essentially increases from right to left. So that's the early stage of cosmic dawn. This is the late stage. And just to let you know that we stopped ionization at only 10%. We didn't go into the reionization era. I will talk about reionization later. Here, the focus was only to see how these two, the Lyman alpha coupling and X-ray heating, impact the 21 centimeter bispectrum. So what we see on the right-hand side is the squeezed limit bispectrum as a function of redshift. for a significantly large length scale. K1 is 0.16 MPC inverse. So what we see that initially the amplitude of the bispectrum monotonically increases and it is negative. Why it is so? To understand that, we went back into the literature and looked into some analytical models or predictions for 21 centimeter bispectrum, not necessarily for cosmic dawn, but for epoch of reionization, where these authors have predicted that if you have a uniformly heated neutral region and if you have ionized hole into that, inside that, spherical holes into that, then you will get a 21 centimeter fluctuation, which will be minus of the window function for a spherical top hat. And then if these ionized spheres are non-overlapping and distributed randomly, then you will essentially sum over their phase centers or the sphere centers. So that will give you a delta 21 negative. So you can go ahead and predict the power spectrum for this, it will be positive. And if you calculate the bispectrum for this, it will be negative. However, our situation is different, right? So we have a cold Lyman alpha uncoupled and neutral region. And on top of that, we have a few sources around which we have Lyman alpha coupled. So you have essentially a weak negative background. On top, you have strong negative signal in, let's say, sphere or whatever shape you can imagine. We are not interested in the shape. We are more interested in the sign of the density, 21 centimeter fluctuation. So it will give us a large scale signal, which is negative essentially. So that kind of explains why we have this signal negative. And as the Lyman alpha coupling increases around the sources and new sources are produced, essentially the amplitude of fluctuation also increases and you see kind of Lyman alpha coupled IgM here. And then it eventually saturates. And in this regime, essentially this bispectrum follows the matter bispectrum if you just multiply a negative sign with it, with proper normalization as well. Okay, so the next model, we had Lyman alpha coupling and ionization on top of it. No heating, by the way. So what happens in this case, we have Lyman alpha coupled IgM until here. Sorry, Lyman alpha coupling dominant IgM until here up to redshift 14 or so, where both these models actually match with each other, beyond which ionization kind of takes over gradually. And now the bispectrum shows a sign change and it becomes negative. So we go back to our toy model and we ask the question, what should be the sign? So we have a cold Lyman alpha coupled neutral background. On top, we have ionized regions. So ionized regions are of zero signal. The signal is coming from the outside of the ionized region, from the neutral hydrogen itself. So it's a zero signal in a negative background. So large scale signal will be positive in the Fourier domain. So you multiply 3 positive delta 21. That's why you get this red dashed curve going up and crossing the zero here. Next, in the third model, we include heating, but now we purposefully kept the Lyman alpha saturated from the beginning. So the sources that produce X-ray, that will produce the heating in the IgM, they are very few at very early times. So as they grew in number and essentially in the population, so the heating gradually takes over later on around here. So initially the bispectrum, this purple line, stays kind of flat, and then heating takes over. It creates a warmer, less cold IgM around them. And inside that warmer IgM, you have small, tiny heated regions. So that is what is driving the large scale fluctuations here. So eventually, that essentially makes the 21 centimeter fluctuation positive. And that's why we see a positive sign change here. And then the heated regions, as they are growing in size, they eventually will percolate with each other. So as they percolate, there will be leftover cold region in the IgM, which are surrounded by these heated region, which has now become a single heated region, interconnected heated region. So now you will have a scenario, something like this. You have a heated and neutral IgM. On top, you have very few Lyman alpha coupled regions. So that is a negative signal in a positive background. So your large scale signal will be negative. So bispectrum will be negative. So that's why we get this second sign change. Further, as the heating goes on, this leftover cold regions gradually gets heated up. So the fluctuation overall, we are always measuring the fluctuation in the signal. So overall contrast in the signal goes down. That's why the amplitude of bispectrum also goes down. Now let's get into our realistic picture, which is this model C, and that's shown by this dashed green line, which more or less follows the story so far. So initially you have Lyman alpha coupling dominant, and then heating takes over. Then it is more or less heated regions that are playing the major role, and they get interconnected, and eventually they reduce the cold regions to something, let's say, mildly heated, and so on. So this part of the story is dominated by Lyman alpha coupling, and this part is dominated by heating. Now, you can ask the question, well, you can see the similar kind of signature probably in power spectrum as well. Well, if you look at the power spectra for all of these models, yes, there are certain subtle features in this green curve you can see. But given the fact that to identify those subtle features, you have to actually probe the power spectrum at a significantly large number of redshifts, as well as your error bar in the power spectrum has to be significantly small as well. So in this case, the sign change gives a better idea, a more conclusive idea that which process is dominating at what cosmic time. So further, one can ask the question, well, how robust these results are? If you increase the size of the K bin or shift it to another slightly larger K value, will this thing still remain same? The answer is yes. More or less, the basic features remain same. And what about if I change the parameters of our model? So let's say if I increase the X-ray production efficiency, what happens then? If I change the minimum halo mass, which can host a source, if I change those things, even then the features remain same. The only thing that differs is essentially the whole feature shifts in time or redshift. So essentially, these features can be used to probe the cosmic dawn history as well. In principle, we haven't done that yet. So the moral of the story is that the bispectrum is the potential probe of non-Gaussianity and can probe, I have the second part, don't worry. So can probe the IgM physics that sources this non-Gaussianity in the signal. And the bispectrum features can be used as a confirmative test. Let's say you have detected the 21 centimeter signal in power spectra. Just to be sure, you can do a cross correlation, or there is another option with the 21 centimeter itself. You can try to estimate the bispectrum and see these sign changes if you can. And that will tell you whether you have detected the signal or not. And the sign of the bispectrum can tell us about the relative contrast in the signal fluctuation with respect to the background. And that essentially works as a smoking gun. The sign of the sign and sign change works as a smoking gun of the dominant physical process in the IG. Now, moving to the epoch of reionization. So given the bispectrum, one would like to know if you try to estimate the parameters of EOR using bispectrum instead of power spectrum, how good that would be. So people have tried to do that. What we tried slightly differently is the following. We tried to use all possible unique triangle shapes into our parameter estimation parameter estimation pipeline, essentially. So there is a small, okay, got stuck. Yeah, there is a small bottleneck if you try to do that, because these bispectrum calculations are pretty time consuming computationally. So what we tried to do, and the simulations are also time consuming. So what we tried to do instead, we tried to build an ANN-based emulator, which can emulate the bispectrum for a large parameter space. In this particular case, we considered 3 usual parameters of EOR. I will get into that, and use that ANN-trained emulator as our model in our Bayesian inference pipeline and try to estimate the parameters for UR. So the usual 3 parameters that I was talking about are minimum halo mass that can host a source, a photon source, ionizing photon efficiency, ionization efficiency of the source, which essentially includes the star formation, escape fraction, et cetera, because all those parameters are degenerate, so you can combine them into one, and mean free path of the UV photons, because UV photons are the dominant, let's say, source for ionization during the UR. So what we did, we looked at a reasonably large parameter space for these 3 parameters, and then sampled them using Latin hypercube sampling method. The different colors actually show the corresponding average, mass average neutral fraction that you will get if you set your parameters to those values if you do the simulation. So we had some 550 such samples for which we had simulated the signal, then the bispectrum, and for all unique triangles, shapes. And we used out of them 530 as our essentially training set, and 20 were kept as test set. The accuracy that we achieved is somewhere around 90%. Probably we need larger training set, but the simulations were pretty time consuming, so we had to stop at a certain point. And we kind of went ahead with this kind of accuracy. And these are the emulated bispectrum. So you can see the K1 value, that is the largest arms, largest K arms value on top. And this is essentially K2 by K1, and this is the cos theta between the 2 arms, K1 and K2. So the top one is from the simulations, and the bottom one is from the emulation. More or less, they look same, but there is a 10% difference. So once we had those emulators, we essentially pushed them into our Bayesian inference pipeline and did guided random walk within the parameter space and estimated the parameters. What we found is kind of a confirmation of what we initially thought is true. Essentially, it is very difficult to put a strong constraint on this mean free path parameter. This has already been established in literature, but you can put a tighter constraint on the ionizing efficiency and minimum halo mass in these 2 example sets. And those constraints are tighter than what you can get from the power spectrum or what you can get from a specific set of triangle shape. For example, here we chose the isosceles triangle bispectra because that is what has been used in the literature mostly. The next question that we wanted to ask, what if we drastically change the reionization model altogether? So if we change the reionization model altogether, the topology of these 21 centimeter fluctuation will be significantly different. If that's the case, what about the bispectrum? Does bispectrum has any signature of this topology? Are those signatures significant enough, or compared to power spectrum, are they better? So to answer that question, we essentially had this set of models of reionization, and here we tested them for their evolution of topology. So essentially what we looked for is that the time or the state of the IgM when the ionized region percolate with each other and become one single interconnected ionized region. So we used something called largest cluster statistics that is being used in galaxy redshift survey analysis quite a lot to identify the filament sheets, etc. So we found that these 6 models, which are represented by these 6 different colored lines, essentially percolate at different times. 3 of them kind of percolate at almost at the same state of average neutral fraction in the IgM. And these are the 2 students who essentially worked on this. Then a current PhD student essentially took up from there, and he calculated the squeezed limit bispectrum first, because that's easy to probably understand, and looked at the bispectra. And indeed, some of them actually evolve similarly compared to the other models. We are still at a preliminary stage, so we still do not have a confirmative interpretation of these bispectra. but we looked at the robustness of this signature as well at different K modes. Yeah, I'll finish in a minute. And what we found that they are kind of consistent. Next, something came up as a basically byproduct of something similar to what Hamza has already mentioned, that one of my PhD students was looking for what is the impact on C2 power spectrum if you are doing C2 intensity mapping. And if you have, let's say, astrophysical scatter in the luminosity of C2 line that you are getting from these galaxies, even if you keep the halo mass same. So this work was done using the SIMBA and SIGAME combined simulation where the chemistry has been included. And these dots are essentially the three-tiered simulation in three different volumes with three different mass resolution. And what we tried to fit them with various kinds of models, and we found one kind of a robust model, which is essentially fitting the most probable value of the bin. And we looked at the C2 autocorrelation power spectrum, and there is some impact. But that essentially gave rise to the question, C2 is related to star formation efficiency. So if star formation efficiency has a scatter, how does that impact the 21 centimeter signal from the same era? If you look at the literature, there are papers by Sultan Hassan et al., and they have found that the power spectrum doesn't have that much of an effect, even if you include this scatter. We thought, okay, if the scatter introduces additional non-Gaussianity, what happens to the bispectrum? So let us look at that. So we, just for a test case, we assumed a log normal scatter with our star formation efficiency, and we generated several realizations, I think 50 or so, and of our simulated 21 centimeter signal, and then calculated the bispectrum. So then from these scatter, the maps, which includes the star formation efficiency scatter. And then we estimated the ensemble average of these bispectrum from these realizations and compared it with a non-scatter scenario. That kind of shows our impact, how much ensemble, how much impact is there due to the scatter. However, you can see that at very large K modes, you probably have some impact. But this particular figure is not necessarily telling you the whole story. You need to know whether these impacts are statistically significant or not. If the sigma or within that bin is big enough or small enough to make them statistically significant. So we estimated that as well and found out actually the large K modes, that is small scales at higher neutral fraction, have more impact compared to the lower neutral fraction. That is kind of intuitive because these scatters at the early stages of the reionization will produce more fluctuation because the sources are far away, the ionized regions are smaller, so its impact will be higher at higher neutral fraction. So this is, the column is essentially the neutral fraction. Rows are K1 modes. So at higher neutral fraction, you have more impact. At lower neutral fraction, you have less of an impact, at least statistically significant. So we looked at the power spectrum as well, and not so surprisingly, because it is kind of a confirmation of what is there in the literature, that power spectrum doesn't have statistically significant impact. The regions where it shows statistically significant impact, actually the impact is less than 5%. So indeed, the scatter introduces some non-Gaussianity, but that is basically in intermediate or small scale fluctuation, not necessarily at the large scale. So that is more or less the 3 points for these three works I have mentioned here, that you can put a tighter constraint on your parameters using 21 centimeter bispectrum, and different reionization scenario may have different signatures on 21 centimeter bispectrum from UOR, and the scatter in the SFR halo mass relationship may induce additional non-Gaussianity that may change your small scale bispectrum to some extent. Yeah. I'll stop here with this message that bispectrum is complex. That's why it's fun.
Questions?
In the first part of your talk, you always talked about TCMB,
Yeah.
but there could in principle be some radio emission that might be clumpy. And
Okay,
then
yeah,
the
so
thing that matters is the
I
radio flux.
essentially assumed a scenario where those radio emissions has been removed from the data. So there is no foreground, etc. So you are talking about extremely bright radio sources.
I'm talking about extremely bright radio sources that are actually changing the radiation field at the location of other hydrogens so that the relevant radiation is not.
So you are assuming that even at that early stage of the universe, there are radio sources which are essentially affecting the, but if there are, okay.
Or even the ones that are doing the ionization could be producing radio flux that's affecting the local environment around them.
Yeah, but the idea is that we are targeting a line emission. So the radio flux you were talking about, that would be more of a, let's say, broadband emission, right? So that will be smooth in frequency. So in principle, even if it is there, that can be removed by some sort of foreground modeling. I'm not saying it's easy, but in principle, it can be. Am I getting your point?
I'll talk to you after. It's not worth talking.
Oh, okay, fine.
More questions?
So I guess in this context of how much information, extra information you get from the bispectrum, I suppose one issue is how robust are your error bars on the bispectrum measurement. So for galaxy surveys now with Euclid and all, they've been a lot of focused work on this. So is there something similar happening in with 21 centimeter expectations? Okay. And have you done anything?
So you are essentially talking about which error bar? Is it due to the cosmic variance or the sample variance within the bin? Which one you were particularly?
Well, if you're projecting something for, let's say, SK,
right?
So then, as a function of scale, has anybody studied which errors are more important and how you estimate these covariances?
Right. So what we have included here is sample variance. So within a, let's say, triangle bin, how many triangles are there? That estimate has, how does that affect our essentially sample variance? That has been included. And the effect of noise, the system noise has been included. But what has not been included is the impact of cosmic variance. So for that, you need many realizations, and you need to then calculate essentially the variance of the realization.
And you also account for full covariances between bins with the survey masks.
That has not been done. I think that has not been done. No. That has to be done before claiming anything.
Hello. The question is regarding foregrounds. So what is the, is there any idea of what the foregrounds will look like if we calculate the bispectrum?
Well, the foregrounds are affecting your delta 21 here as well, the Fourier transform of your brightness temperature fluctuation, right? So just like in case of power spectrum, you draw the foreground within this cylindrical power spectrum space, perpendicular PK parallel space, and you show the foreground wedge. Similarly, in the bispectrum, if you can plot the K1, K2, K3 vectors in the same fashion, there will be a bispectrum foreground wedge as well. However, its shape would be pretty complicated, and I have not calculated.
Okay, thanks.
I don't think it is very trivial. Maybe you can do that.
Thanks.
Any last questions? If not, let's thank Suman again and all the speakers for this workshop.